Colleagues, please switch on the broadcasting. Good afternoon, distinguished colleagues and guests. May I declare the meeting of the Dissertation Board open to review the dissertation submitted by Dmitry Kuruch under the title Quantum Chemical Calculations of Perovskite-based Nanostructures in the specialty 010001 in Organic Chemistry. Under the relevant decree of St. Petersburg State University, I was appointed as the chairman of this dissertation board. May I introduce my colleagues and members of the dissertation board. Pavel Dyachkov, the head employer of the Laboratory of Chemistry, a professor. Yuri Zhukovsky, head of the Laboratory of the Solid Body Physics Institute, professor. Sergei Lopatin, Inorganic Chemistry Department professor of St. Petersburg State University. Ilya Tupitsin, professor of Quantum Mechanics Department of St. Petersburg State University. And online, we are having Alexander Schluger, professor of the London University College, Great Britain. First and foremost, I would like to note that according to the federal law on science and public policy in science, research and education, St. Petersburg State University was granted an exceptional right to award academic degrees. A relevant decree was issued in St. Petersburg State University, and this decree was issued on September 1, 2016, number 60-21/1. According to this decree, the meeting of a dissertation board is considered valid if no less than 2/3 of its appointed composition is present, but no less than 4 members. Today we are having 6 members of the board, and the dissertation board consists of 6 members. Now I would like to suggest the following procedure of the meeting. Please keep the options in mind. Those are valid for all those who are present today. The dissertation board meeting should last no more than 2 hours. First, a brief report of the chairman is pronounced, and the chairman reports on the key documents submitted by the defendant. Then the brief report of the defendant on his dissertation, on his research, is to follow, and then questions. Then the chairman declares the reviews that were submitted to the dissertation board, and members of the dissertation board take turns in declaring their positions, their recommendations to the defendant, no more than 10 minutes per speaker, to be followed by the defendant's replies to all the members of the dissertation board, no more than 15 minutes overall. Next comes the open discussions. Members of the audience who are not members of the dissertation board take turns in declaring their positions or recommendations strictly on the topic of the findings. No more than 5 minutes per speaker. All those wishing to take the floor from the audience, please register in the list beforehand. Point 8. Defendant's replies to the questions of the members of the audience, no more than 5 minutes. And the address of the research supervisor, no more than 5 minutes. 5 minutes break before open voting to vote whether the defendant has passed or failed, and whether to award the defendant with the aspired academic degree. At this time, no broadcasting is allowed. Next comes open voting by name, And the results of the voting are recorded into the minutes of the meeting. Last comes the closing address of the defendant, 5 minutes maximum. So this is the procedure. This is what it looks like. Before we start implementing the procedure, please, I urge you to switch off your mobile devices. Thank you for compliance in advance. I also inform you that we are having online broadcasting on the St. Petersburg State University website. There is also simultaneous interpretation from Russian into English and English into Russian. The dissertation submitted by Dmitry Kuruch in the specialty 020001 Inorganic Chemistry, Quantum Chemical Calculations of Perovskite-based Nanostructures, submitted in conformity to PhD requirements in chemistry, was accepted to the Dissertation Board in September 2017 under relevant decree. The defendant has presented to the Secretary of the Dissertation Board the following documents. Application addressed to Rector Kropotchev, shall we go on? Addressed to Rector Kropotchev, dated September 6, 2017. Colleagues, I suggest we make a technical break because we have lost the online connection with Professor Schluger. Professor Schluger, welcome. You are with us again. That's great. So I go on, speaking about the documents that were submitted by the defendant to the Dissertation Board. The report of the research supervisor, head of the Quantum Chemistry Department, Doctor of Physics, Robert Everestov. A list of publications, including 6 papers that reflect all the key findings of the dissertation, including those registered with the Web of Science. A certificate certifying that the defendant has successfully passed the relevant postgraduate exams, and a diploma issued by St. Petersburg State University. The dissertation in hard and soft copy. The dissertation is drafted according to relevant requirements. I should note that all the mentioned documents are in compliance with the decree aforementioned. So I have read out all the official normative part of the procedure. Now I would like to give the floor to Dmitry Kuruch. 20 minutes is your time limit.
Dear ladies and gentlemen, dear esteemed members of the Dissertation Council, dear guests, the topic of my research is the quantum chemical calculations of nanostructures based on perovskites. And I would like to talk about the key issues. Currently, perovskites are widely studied objects demonstrating unique electronic, magnetic, and optical properties that underlie the work of many existing and potential devices. nanoscale systems are implemented in such objects as nanobytes, nanorods, and nanocrystals, and such nanomaterials based on. First, I'm going to talk about the use, then the calculations of 3D cubes. First, I will talk about the calculation technique, then about the calculations of nanolayers and nanostructures. In the end, I will talk about the absorption of water on the surface of nanolayers and nanotubes. The computer program Crystal was used to perform the calculations. Quantum chemical calculations were performed by the TFT method using the Hilbert exchange correlation function FBEO. The functional is successfully used in calculations of the volume and surface properties of perovskites, and also reproduces the parameters of hydrogen bonds with the participation of water molecules to describe the interaction of the core and valence electrons of BAY, zirconium, etc. Atoms stolen creandable pseudo-potentials with small cores were used. For atoms of oxygen and hydrogen, a full electron basis was used. Perovskites can exist in different phase modifications. The cubic structure inherent in most perovskites is characterized by the spatial group PM3M. For the zirconiums, zirconium strontium and O3 crystal, the orthorhombic modification with the spatial group PB and M was also considered. Bulk crystals were used primarily as test systems to verify the reliability of the chosen calculation method. And the calculated lattice parameters, moduli of elasticity, atomization energies, and the widths of forbidden bands agree well with the available experimental data. The models of nanolayers studied in this work can be divided into two types. First, simulation of precursor nanolayers for the further modeling of nanotubes, and two, modeling of defective nanolayers to study the influence of impurities on surface properties. The alternating one atomic planes in the bulk crystal of perovskite AbO3 have a different composition. Stoichiometric Y-substitute nanolayers consisting of 9 alternating O1 atomic planes were considered to model defective surfaces. It is known that Y3 plus ions replace zirconium-4 or HA4 plus zirconium-4 plus HA4 plus with the formation of oxygen vacancies. Therefore, BO2 terminated O1 surfaces are most suitable for modeling surface fixes. Using 2x2 and 3x3 extended 3D cells, two models were constructed. First without inversion and with a vacancy only on one surface of the plate, and two with vacancies on opposite sides of the plate. In this case, the inversion symmetry ensures the equivalence of both surfaces. Different positions of the substituted atoms near the vacancy were considered for both models. On the basis of the Y-substituted surface, the mechanism of oxygen vacancy migration was studied. The transition state was obtained with a symmetry constraint, but with full optimization. If we remove the symmetry constraint, then with a small shift, oxygen migrates to the initial or final state. Thus, we can assume that this state corresponds to a saddle point on the surface of the potential energy. The calculated energy barriers are small, so that migration of oxygen is possible at higher temperatures. The initial structure of a nano tube can be obtained as a result of the folding of a layer, which means the construction of cylindrical walls of HC by folding two periodic crystalline layers. In all, the considered considered layers, the energy of folding tends to 0 as the diameter of the NT increases, since the value of the total energy per unit NT tends to the corresponding value of the nano layer. In the case of AO terminated 4-layer NTs with chirality, spontaneous stratification into two shells is observed for n smaller or equal 16 for SR ZR03 and BSR03 NT. The inner shell consists of one ZR02 layer, and the outer shell consists of three ZR02 layers. And that's figure 6a. The internal SWNT zirconium OT has hexagonal morphology of the zigzag type. Such a fibration is possible in connection with the close translational periods of NT from zirconiates and NT from zirconium oxide. To estimate the stability of stratified of DSNT by the energies of ESPs between two NTs were calculated. The negative binding energies of the constituent OCs suggest that stratified DWNT is energetically more advantageous than the two isolated SWNTs at N greater than 16 NTs. 16 NTs do not exfoliate and show high energy of formation. The stratification was not observed in the case of BATI03 NT, apparently due to the incommensurability of the periods of NT from TiO2 and NT from BATI03. Stratification of NT is one of the ways to reduce the flexation stress of NTs folded from a 4-layer plate. This can also be done by lowering the symmetry. In this paper, two possibilities are considered. One, a decrease in the order of the rotation axis, and two, folding of nanolayers from the orthorhombic face only for SR-ZR03. When the order of the screw of rotary axis is reduced, the NT undergoes a noticeable reconstruction. The HC cross-sectional structure changes from a circle to a polygon consisting of a 4-layer blocks that are partially separated or slightly bent. The number of blocks of NT is equal to the new order of the axis of rotation. The absorption of water molecules on the surface of crystals and nanoscale crystallize is a physical phenomenon that ultimately determines many of the physical and chemical properties of the real surface of these objects, as well as their stability. Calculations of water absorptions on BaHFO3 and ZrO3 surfaces were carried out using both primitive and doubled extended elementary cells. This means that there are two electropositive absorption centers in the unit cell, and consequently two surface coatings can be considered depending on whether the water molecules are occupied by a single absorption center, a semi-monolayer, or both a monolayer. Simulation of mixed absorption is possible only when using the expanded cell. In this case, one of the water molecules per unit cell retains the molecular form, and the other dissociates. Energy absorption of water suggests that the interaction of water with the surface is a rather exothermic process. On the Y substitute, the surface of water molecule is absorbed to the place of the oxygen vacancy. The different initial locations of the water molecule over the substitute surface of barium, zirconium 03 and BaHFO3 were considered: one over the zirconium and HF atom, and two above the Y atom, and three above the oxygen vacancy. In all the cases considered, the water molecule dissociates to form two bridged hydroxyl groups. The proton-bridged oxygen rises above the ZrY and or HFY plane, therefore changing the surface structure around the place where the vacancy was located. The interaction of water with the surface is a highly exothermic process. The energy gain in the dissociative absorption of water exceeds the cost of generating an oxygen vacancy by about 100 kJ per mole, of the order of -1. The value of the water absorption energy depends on the orientation of the resulting bridged hydroxyls. In the first case, the bridged hydroxyls are bonded to one common Zr or HF atom, while in the second case to the common atom Y. It should be noted that the absorption energy in the first case is higher than in the second. And the third calculated case, the bridged hydroxyls are parallel to each other and do not have common Zr or HF or Y atoms. The structure is most advantageous. The dissociative absorption energies on the substitute surface of BaZrO3 and BaHFO3 are approximately 2 tums lower. So the on the absorption of water on the surface of the nanotube doesn't lead to the change of structure, and
so those look like the perovskite layer. The hydroterons of the nanotube of the hydrotitanium-2 are cylindrical. They have a highly reconstructed, highly modified surface. The absorption in the fractions between the blocks is more favorable than on the surface of the acid. In this case, the molecular formula of water becomes unstable and the water molecule spontaneously dissociates, absorption at outer surfaces of the nanotube is more favorable than the absorption on the internal surface of the nanotube as well as nanolayers. The width of the marginal area and the valency area as well as the conductivity affect largely the photocatalytic split reaction. The thermodynamics of this reaction depends on the relative position of the limits and is relative to the oxidization potential of water. In case of photocatalytic water decay, only nanotubes with titanium-2 external surface are appropriate. The key findings of the dissertation are reflected on the following slide. The most stable single-wall nanotubes. May I interfere? Is it necessary for you to read out the findings? No, it is not. So let's have them on the screen. Thank you. You have not extended the time limit. Now it's time for questions. Yes, please. Please switch on the mic. So you used standard, right, software. Was it necessary for you to somehow modify the software and the protocols? Did you introduce any modification to the protocols and the software so as to make it more efficient? Thank you for the question, distinguished professor. Well, for my calculations, I made all the basis of all the materials more efficient, and the diffuse function with an exponent of less than 1/10 was excluded out of this set, whereas the rest were optimized for bulk crystals. The F function, I should note, of the barium atom was excluded from the basic set because our calculations showed that it does not affect the key results anyhow. Thank you. I would like to clarify one point. So you declare that there are two editions of the software, Crystal 06, Crystal 09, but we also know Crystal 16 and Crystal 14. So did you check the results against these versions of the software? Well, yes, indeed, we have nanotubes in Crystal 9 and Crystal 14. It is more of a finer point. It's a tricky thing. Thank you very much for the question. Well, actually, the results themselves, the results I compared in my dissertation, were obtained within one type of software. The results obtained by way of different software programs and protocols were not compared. But I think that this is my homework to do in the future so as to assess the accuracy of each software. So you mentioned version 6 and version 9. Did you do any preliminary calculations in Crystal 14? Well, the calculations of no-doped and doped surfaces were calculated in Crystal 6, whereas the calculations with nanotubes were done in Crystal 9 because it was issued by that time. Colleagues, more questions? Yes, please. Two questions. Two general questions. Could you please assess your personal contribution? Because I see there's a huge work done lots of calculations. So it's very difficult for me to understand whether you did it alone or you were assisted by someone. Just your personal contribution in percentages, 70%, 80%. Well, most of the calculations were done by myself personally. Well, the results and the findings were formulated together with my research supervisor. Well, I got it, thank you. And one minor question. Did you do any analysis of chemical parameters based on the covalency of the atoms? Because I know this is just chemical work, right? Well, when we studied the surfaces, we did not do this kind of analysis. So it is just not in the focus of my findings, but it is there. It was done in the process of calculations. Okay, thank you. Do you hear us, Professor Schluger? I have a couple of questions. The first question is quite general. I'm truly impressed by the number of findings, as well as the number of conclusions, what you declare about multifaceted objects and about the nanolayers. I wanted to understand, what were you guided by when you chose the chemical potential of oxygen, for example, when you had to assess the stability of these objects and made a conclusion that they are stable? Well, actually, the stability criteria was assessed by the energy of formation. The more negative the formation energy of the structures, the more stable these structures were considered. But the formation energy is included into the chemical potential of the objects. For example, you can choose the chemical potential of oxygen, and depending how you choose it, the formations, the results will change. So what criteria, what parameters were you guided by in choosing the chemical potential of materials? Well, frankly speaking, it's difficult for me to answer this question. My next question is as follows. So we discussed the crystal program and its various versions. It is quite a powerful program to calculate the electronic structure. However, your report says very few words about the basic structure. It is geometric structure and the stability of objects primarily. What about electronic structure? Did you attempt to compare it with some other data? To what extent is it reproducible? And in what extent is it relevant to us, or is it irrelevant? Thank you very much for the question. Well, once again, the electronic structure for some objects was calculated, as far as I remember, but I do not focus on this aspect in my dissertation. Well, this is, once again, something to be done in the future. Thank you. Professor Schluger, are you satisfied with the questions? Yes, I am. Thank you. Well, I think that the quantum calculations should be forecastable and interpretable. You know all too well the results of practical experiments. Therefore, my question, your research, is it more of an interpretation or is it more of a forecast to those who are going to stage experiments? I mean, you provide them with some calculation or protocol, and they will use this protocol for their calculations. Thank you very much for the question. Well, actually, in general, these calculations provide a forecast, because the real objects that we observe are more numerous than those that I analyze in my dissertation. So I make calculations on just a set of nanotubes, so as those who are going to set up experiments can use these calculations on different types of nanotubes. A follow-up to my question is, well, naturally researchers should refer to works of their predecessors. I believe you know all too well the research papers on your topic as well as on other topic. How often do those who set up experiments refer to theoretic research? Thank you for the question. Well, this is not something that was in my focus. Well, I believe that such minor details are there, but I cannot give a certain answer. My question will be a follow-up to the question of the previous speaker. I'm an engineer of experiments rather than a man of theory. So, therefore, my question. So you brilliantly demonstrated quantum physics calculations. And there are two dimensions, the forecasts and the criteria of search. And the second thing are the models that can explain some particular process. I'm mostly interested in the state of protons in water. And here I believe that the question of the previous speaker can be answered in the following way. More often, they refer to not something that is forecastable, but something that can provide an explanation to some specific phenomenon. So therefore, my questions, will your calculations assist anyhow to those who are building these forecasts in how materials would behave in particular conditions? Thank you very much for the question. I believe that such research can assist those who are dealing with experiments because there is a high energy barrier for protons when they are transformed from the surface to the internal layer. And therefore, we need a more detailed dispersity, a higher grade of dispersion. Well, this is what about the state of material. As for the nanotubes, those are just a nanoparticle. So what happens there? If we do not observe the nanotubes, but nanoparticles instead, 4 nanometers, and so on and so forth. Well, I cannot provide the answer to your question right away, but this is a topic for future research on objects of smaller scale. Well, modeling of coal nanotubes, of silver nanotubes. Well, it is a difficult task, I know, because of it's difficult to achieve the temperatures required. Colleagues, do we have any more questions? Professor Schluger, do you have any questions? No, I don't have any. Thank you. Thank you. Well, please, Mr. Kuruch, you can take a seat. Colleagues, we do not have any external reports, and now we proceed on to declaring the report submitted by members of the dissertation board. Professor Dyachkov, well, let's follow the alphabet order, the Russian alphabet order. Colleagues, but please be short. Please focus on key aspects and stay focused on some critical remarks and recommendations and not on the contents of the dissertation, because all of the reports are downloaded to St. Petersburg State University website. Thank you.
Представленная диссертация лежит в области прикладной квантовой химии.
Well, the dissertation is on quantum physics, and it looks at highly exciting objects, nanotubes and clusters of nanotubes. The dissertation, the scope of the dissertation is vast. Of most interest is the structure of these composite materials. The doped properties are analyzed, and their effect on the properties of the materials, as well as the effect of the solvent on non-organic nanotubes. And to wrap up with looking at the catalysis effects and the hydrogen formation. The dissertation is highly innovative. As a result, we are presented with highly relevant information. The validity of the results is undoubtful because the defendant uses top-notch software and methods. I don't have any substantial critical remarks. Therefore, I urge all the members of the dissertation board. Well, you can urge us later. Thank you very much. Thank you very much, Professor Dyachkov. Thank you.
I'm not going to talk about all the positive sides of this research. This is, clear. So, and this research is a quite comprehensive one. It talks about the use of methods of quantum chemistry to the modeling of 2D nano thin plates tempered by yttrium. And I know that it's very difficult to set the goal and to justify it, and because there's a lot of competition in this area, and therefore the researcher must think about very hard. And in this case, your research is very valuable. So if we talk about the nanocrystal that you use, I could make some comments about how this could be improved. Well, this is a very good volume of the data that you're using, and therefore the methods that you used are quite valuable, and of course you look at all the nano-thin nanotubes, and especially defective engineering, and there are no ideal objects, and you have to understand which defects there are, and to look at real synthesis of how you can synthesize defective features and improve and get a better result. So this is a highly valuable feature of your work that would appeal potential readers. And about photocatalysis that you used, the conclusions of how to use these systems, how to apply these systems is very good too. It's of high interest. When 100% 3D materials don't exist, but using your data and your conclusions, we could gets very good applications. But also, I would like to draw your attention to some comments and some maybe technical nature. So, in the introduction, I think that if we talk about metals, pages 5 and 18, you have to concretize, and you have to add transitional before metals. That's line 6 and 8. But also in the methodological part of the paper, the first chapter, pages 7 to 8, well, it's not clear whether the author optimized basic functions for better compliance of the conformity of the parameters of the binary ZrO2, YO2, and HFO2 oxides, and also BaTiO3, SrTiO3 perovskites to the data of the experiment and other theoretical works. And of course, there's a grammatical error on page 7. Also, in section 2.2, the statement that the termination that both terminations appear simultaneously when surface is formed. You could have improved on that and specify what you mean. And also in the second second paragraph on the same page, symmetrically terminated without a hyphen, you write, and also you omitted an interval between OV1 and 1, and then section 2.3. Again, if the nanoplates BrZrO2 and BaHFO2 are wide-tempered, why do analogous structures not get examined for nanotubes? Section 2.4 says the absorption of water can be chemoabsorption, and you could better use the term physico-chemical, and also you could write the oxygen molecules of water. Section 2.5, just as at the beginning of section 2.3, why wouldn't you supply a drawing, figures to clarify, and also there's another one. Another comment on page 52, on page on figure 22 on page 49, instead of the second A, you should have put a B. That's page 50. In the conclusion, when we talk about the reverse BA termination, the opposite BA termination, BAO termination, you should have replaced tubular instead of tabular. And there's also the bibliography, some errors there. You have physical instead of, and then there's a type of physical. Well, these are all stylistic errors and punctuation, but on the whole, the validity of the results are not questionable at all, and I think that the use of different programs that you used is also justified, and therefore I would like to state that that the dissertation work by Kuruch Dmitry Dmitrievich is a conclusive research piece and complies with the standards of St. Peter's State University on the degrees.
Well, in my research, I note the relevance and the practical relevance and validity of the dissertation, as well as the high quality of results obtained. All the previous speakers have noted the positive aspects of the dissertation, and I support them. I would like to merely focus on some critical aspects. All of my critical aspects are made from the position of implementing these results within an experiment. I believe that the introduction fails to substantially focus on the properties of perovskite surfaces as well as the surfaces of synthesized nanotubes. The dissertation fails to include all the experimental data that are there at present. The research mentions the results of the properties of perovskite surfaces. However, there is no data on conductivity. The energy data on absorption on the surface of perovskites does not match the results of direct or indirect measures. So in the dissertation, what we see is the energy parameters without any tolerances. There were several tables. In some tables, the data is as precise as to the single units, whereas in other tables, the data is done up to the tenths and the deciles. Well, but I did not see how the defendant uses these data, so it is not mentioned in the following text of the dissertation. Well, and also the previous speakers noted some grammatical mistakes and misprints. Despite all the aforementioned critical remarks, I believe that this is a worthy piece of research and it is in compliance with the requirements to this type of academic works, whereas the defendant deserves to be awarded the aspired academic degree in inorganic chemistry. Thank you very much. Next speaker, Professor Tupitsin. Well, I would like to follow the key points of my report. Well, undoubtedly, the research is relevant. Next is the relevancy of methods, and of course, they are relevant and very well justified. Here, I also would like to add that, as the defendant declared, the key method is the density functionality potential, and the LKO method. Here, I, as a physicist, would like to note that the bases that was used are the most suitable ones because contemporary methods, general works on physics, reside to flat wave bases. However, those are not as well adjusted to analyze chemical properties because these bases are localized across the entire crystal material, and in this respect, the crystal software is very well justified. It is a good choice. I also would like to note that overall, the text is logical and it reads well, but There are some minor flaws that are there in any kind of research. And here I would like to note that the first chapter, looking at theoretical methods, this chapter to me as a physicist was the most exciting one. I think that this chapter is too short. You could have included more data. There is only more than 1 page describing the methods. I also would like to note that the first chapter should have included some more description about heavy atoms and the pseudo-potentials that should have been used here, or rather the effective potentials of the bases should have been structured with a focus on the spin orbit. And after all, we do not know whether you have included the spin orbit there or not. And it is only references that indicate that relativist heavy potentials were used, which is right, in my point of view. As for the optimization description, the optimization of geometry, here I would like to note that the following phrase, elementary cell units were optimized, and here you should clarify whether symmetry was preserved or not. As for the second chapter, that features some exciting findings of a vast research. Well, here a lot has been said about it. It is a very worthy chapter. And now I would like to wrap up about all my critical remarks. Well, some substantial critical remarks that could invalidate the findings are absent. There are some minor flaws. They do not invalidate the overall positive impression, including the fact that you do not mention the spin orbit and other relativist effects for heavy atoms. You fail to discuss the symmetry issue in geometry optimization. And lastly, this is a regular thing, there are some inaccurate, failing terms and language that could have been made better. Well, then I once again note the relevance of the results and the fact that they are justified. These results can be used in several lectures on nanodynamics of nanotubes and nanocrystals. And lastly, I also note the aspects that make this dissertation highly valuable. The defendant deserves to be awarded the aspired academic degree. And Professor Schluger, your report.
Dear, I would like to say, first of all, I agree with that the crystal and that the is justified because of the local basis and the. I would like to say that, as you said, the author focused on the structure, the use of local functional is not really justified, and this could have been done better in a cheaper way. And maybe for our systems, I cite examples what we could use energy fields for that for comparison that could be used. The non-local functional is quite reliable, but there's a lack of flexibility in this method than the method that could be used with the same accuracy but more flexible. I would like to say also that the defective surfaces that was used were calculated according to high concentrations on the surface, and they don't have the surface segregation. I cite other works which provide some expertise, but I also agree with the previous speakers where they question that the author knows some other theoretical literature in the same field, and in 2.2.2 it talk about several oxides. I refer to my questions that I already asked. There was a lot of controversy on this, because there's an influence of the oxygen oxide, and so this research could have been done, this calculation, to include temperature, and this could have been done with better care. As far as the 2.3, I also think that the volume of the work was great, and the accent on the structure and the chirality gives a lot of valuable information about structure and stability of nanostructure nanotubes on the basis of energy folding. But as in the case of thin slabs, the free energy of this system, well, the author doesn't take into account of how the free energy of this system depends on the chemical potential of oxygen and metal on the temperature. There's no connection with the experimental conditions of the growth of nanotubes and the features that are important to apply these in the application of these nanotubes. Also, I'd like to say that the tension, especially in the inner surfaces of the multi-wall nanotubes, could be lessened through the formation of defects, such as vacancies in the atomic transfer between the inner and the external surfaces, and it was not taken into account in this work. And I would like to say that the character and the nature of the localization of the states, which is the difference between the energies between the upper and the lower electron states, needs to be taken into account, and this is not discussed, and it could have been a very important contribution. In section 2.4, we have the results of calculations of interaction between water molecules with oxide surfaces in order to assess the accuracy of this prognosis. You have to compare then with the results of experimental measurements of enthalpium absorption, such as, for example, you can find in the journal Serum, and a number of recent theoretical studies, as in the Journal of Physical Chemistry. And in section 2.5, you have results of very comprehensive calculation of the absorption of water. And again, I see that the results are very, very valid for non-defective surfaces. On the whole, I agree that this is a valuable work. Thank you.
Well, I can say that Dmitry is a nestling of Mr. Everestov, who over quite of a time span has been producing brilliant postgraduates, brilliant researchers with high quality dissertation. It's great that the quantum physics department is working closely with those who set up experiments. Why is it for the better? Just because we have spoken a lot about the results and the experimental results that are there and that are yet to come, and that are highly relevant, because lately we have been seeing a lot of new transformations in the nano world. I remember myself as a student when, by setting an experiment, you could create a nano world of your own. So today we see the implementation of theory in experiments. As for the tessonite and the fluorite 3 that we have been looking into for several years, and the experiments allowed us to expand, to improve its properties tenfold. This type of research allows us to establish goals to synthesize the materials that are already there in theory. So this is the star that we should be guided by. The results that were presented to us today are highly relevant because those use both sensitive elements for electrochemical devices, for sensors, for hydrogen conductors, and in fuel rods. This is something that is used across a broad scope of areas. I totally agree with what my colleague said, and I'm not going to focus on all the positive aspects of the defendant. Of most interest to me was the following. In particular, the relevant stability of nanotubes with zirconate strontium, barium zirconate versus barium titanate and zirconium titanate. And there is a correlation between these compounds. Next, the section on the water absorption was the most exciting to me. as well as to look at the prevailing type of water absorption on the internal and external surfaces, because this is highly relevant for those who deals with proton conductors and analyzes the properties of new materials. Of course, there are some points for criticism. I would like to note two of them. Despite the vast amount of calculations devoted to perovskites, the calculations do not feature the properties of perovskite surfaces. And next is that my next point of criticism just echoes the ones that have already been said. I would like also to note some flaws and misprints. I'm not going to repeat them. Next, I would like to say that the dissertation by Mr. Kuruch is highly important for chemistry and material study. It's an important trend today, both for our university and other universities.
Both in the educational process and the conclusion are very important. We're enrolling most master's degree program that is in the field that has to do with nanomaterials and nanotechnology. Is very important aspect, and because we talk about composite materials and economic materials and natural materials, nano hydrogen materials, nanocarbon material, whatever. The Silicon Valley is of course in America. Is located in America, but Chinese are doing something very similar, and so this Carbon Valley is a great field for research for both in the academia and in the theoretical field as well. And of course, I would like to say the mantra, the last words, that on the basis of what I said, Kuruch's research is a conclusive piece of research, and it deserves that the author of this dissertation be awarded the third degree of the kind of sciences in chemistry. Thank you very much. If you have any questions, please, Mr. Kuruch, you have the word, the floor to answer questions and comments. Not more than 15 minutes, please. I would like to say a few words. I agree with all the technical discrepancies that were pointed out. I agree with the critical points, that will further my research. I also would like to thank the reviewers for those, and I would like to address some questions that Sergei Igorevich asked, how the data from table 1 was used. This data and the table are presented because to make it clear how this potential functional can be applicable for calculations, because our parameters agree well with theoretical values, the marginal errors. For each value, we can assess differently. For example, the absorption energy, the folding energy, and new creations, new formations. In some cases, there are 0.10 to the degree of kilojoule, we could have omitted that, of course, but about the pseudo potential, and the optimization of crystal with full symmetry, and in all cases, in most cases, we wanted to retain the largest symmetry, because the nanotubes had a lot of atoms, and the lower the symmetry, the more complicated the calculations are. Yes, thank you very much. That's all. Alexander Leonidovich, have you answered? Maybe I didn't jot down all of them. If Alexander Leonidovich would like to ask me another question or the same question, I don't have any additional questions. Everything was clear. Thank you. It was addressed. Are you all satisfied with the answers? Thank you very much. Dmitry Dmitrievich, please take your seat. Although, since we have guests here, this session, you now have the opportunity and we have some time for you to take the microphone and make a comment. No. So no takers there. So then I would like to give the floor to the research advisor. Please, research supervisor. I understand that the tradition says that I shouldn't talk about the research side of it. I need to talk about the defender, how the work was done. I would just like to say that when we started our work on non-organic nanostructures, when Dmitry Dmitrievich joined the postgraduate course in 2010, and he was one of the first to explore this field, Ivan Nikolaevich knew about this situation with carbon nanotubes, and he has a monograph in the end, and therefore I focused on non-organic, and that was Dmitry Dmitrievich together with me and Andrei Vilovich and Andrei Bandura, who helped to build the program and with all the details. Together with us, he explored this new field, following what the other members of the the carbon nanotubes there's more data. Non-organic nanotubes, there's less data. In Russia, we couldn't find the experts that could discuss these tubes with expertise. The results, because we didn't only focus on perovskites, we are now focusing on layered systems and that are non-organic, and maybe they promise more, but on perovskites, we had a section on perovskites in a Springer monograph, and one of the that was published in 2015. Dmitry Dmitrievich had to explore a very unusual dissymmetry that were known to physicists and chemists in polymers, but not in application to ortho-periodic nanotubes and nanowires. And of course, this was out of the scope of the dissertation, but the calculations could have not been done without using those. And of course, we had discussions. Not everything was clear from the first, but this is a very interesting piece of research. We focused on, and we also wanted to publish in Web of Science or high impact factor publications, and that's what we did. Thank you very much. Unfortunately, you didn't mention that that there was a remark in one of the reviews that quantum chemistry had a great contribution there. In layer by layer nanotubes, we have when we use this approach, we have the folding, and so we use soft chemistry. Then this is a very promising direction of research. This moves us to explore where there's a junction there between what's done in the research and what can be done in this mentioned area. And I would like everyone now to leave the room because we have a temporal break to discuss.
Насколько я понял от Олега Александровича. Нет?
Да. Ага. Ну вот очень приятно, что вы... Я тебе расскажу. Так, коллеги, прошу.
Colleagues, please switch on the broadcasting. So the broadcasting is on. The meeting resumes. May I now put on vote the issue of awarding the aspired academic degree to Dmitry Kuruch. May I remind you that the decision is legitimate if more than half of members of the dissertation board voted in favor of this decision. Your position, Professor Dyachkov, I'm in favor of the dissertation. I'm in favor. Pass. Professor Smirnov. Well, I also join into this position. This work deserves to be awarded the aspired academic degree. Professor Lopatin, I'm in favor. Pass. Professor Tupitsin, I'm in favor. Professor Schluger, I'm in favor. Pass. Thank you. My opinion is in favor. Professor Zhukovsky, I'm in favor. Pass. So out of 6 members of the dissertation board, reviewing the dissertation by Mr. Kuruch, 6 voted in favor, 0 abstentions, 0 fails. Therefore, Dmitry Kuruch is awarded with his part academic degree in inorganic chemistry, a PhD in chemistry. Mr. Kuruch, the floor is yours for the wrap-up address. Thank you so much. I would like to extend my gratitude to all members of the dissertation board for participation, for compliance. I also would like to extend my enormous gratitude to Professor Eva Restov and Andrei Bandura, my consultant for lots of times, my tutor, who actually brought me to the quantum chemistry department. Colleagues, the meeting of the dissertation board is adjourned. Thank you very much. And I extend my specific gratitude to Professor Schluger for being online together with us. We will be happy to see you, more of you here at our dissertations. Thank you so much. Happy New Year. Happy New Year to everyone. Thank you. Goodbye.